Hello everyone, welcome to the lecture series on 8051 microcontroller. In the previous lecture, we had discussed on port 2 and then port 3, and then we had looked into IO bit manipulation programming. Okay, so how these ports, how can we use the ports which are available in 8051 microcontroller to use it as an input port, and then how can we use that particular port as an output port. Okay, so we had looked into a small programs as an examples. uh, the detailed examples we can will go through in the future lectures. Okay, so in today's lecture we shall uh, look into time delay calculations. These time delay calculations are very much important in terms of programming, in terms of real time or real world scenarios. So why actually these time delays are required? Why these calculations are required? Now let us look at this particular example over here. So I'm having 5 different color LEDs, but if you look at this particular scenario, what we can think is that all these colors are glowing, but actually these LEDs are blinking. Okay, that means what? It is turning on and then turning off. Okay, so but to human eye, it is seeing in a such a way that it is seeing in a such a way all these particular LEDs are on. Okay, so why this scenario comes? Even though I have written a program in a such a way that these LEDs should turn off and then turn on, turn off and then turn on. Okay, but that scenario is not happening over here. For our eyes, it is seeing in a such a way that it is totally on. Okay, that is why, because now if you look at our 8051 microcontroller, so basically we are having the clock frequency. What we are having, the clock frequency is, okay, though it is how much? It is 11.0592. Now let me take in terms of calculations, let me take I have 0.592, it is in terms of megahertz. Okay, now if I take, let me take a simple scenario where I'm having a clock of 10 megahertz. If you convert that particular thing to time, so time is nothing but what? This is our frequency. If I convert that thing to time, that is nothing but t is equal to what? T is equal to 1 by f. Okay, this 1 by f, in the sense I'll be getting somewhere around 0.1 microseconds. Okay, so the switching is happening, the turning on and then turning off is happening so fast. It is taking only how much time? It is only taking 0.1 microsecond of time. Okay, the switching is so fast that our bare eyes cannot recognize whether it is switching on or off. So that is the reason. Okay, so for that reason we are not able to make out whether the switching is happening or not. We are feeling like all these particular LEDs, these LEDs what we are having, all these particular LEDs are what? They are turned on. Now if I add some delay, let me add some delay. Okay, now you can see that after that turning on and then turning off, in between that time gap I have added a little bit delay. Okay, now we can make out whether it is, let me consider that I'm having a delay somewhere around 500 millisecond or something like that. Okay, now we can observe there is a switching. Okay, we can clearly observe the switching on and then switching off of these particular LEDs. Now if I add a little more delay, let me take it to be something like 1 second or 2 seconds. Now you can observe that the switching on and then switching off is clearly visible over here. So whenever we are trying to make out any programming in terms of LEDs or in terms of anything, let us take in terms of real-time scenarios. Okay, the things which are visible to human eyes, and if we write down our program in such a way that just the operation, the switching cannot be visible to our eyes, we feel like okay, it is continuously on. This is where our time delays come in picture. Okay, so most of the time if you are we are thinking in terms of uh, real time scenarios, and if our clock frequency is so high, then we need to add delays in order to make sure that it is visible to human eyes. Okay, processing, if you take in terms of processing, that cannot be a problem for clock frequency, but which is if you want to show something to human, okay, if you want to show something to human eyes, then there should be a delay. Okay, so how to write down these delays, and what is the clock frequency of our 8051, that we will discuss in today's lecture. Okay, so basically if you look at 8051, it is having two different clocks, that is one is XTAL1 and then XTAL2. These have been connected to pin number 18 and then pin number 19 in our 8051 clock period. Now since we are writing our programs in terms of assembly level programs, we will be writing in terms of instructions. Okay, now in order to execute this instruction, our processor, our microcontroller takes certain number of clock cycles in order to complete the whole instruction. For original 8051, it takes 12 clock periods in order to complete an instruction. Okay, this 12 clock period, okay, this is nothing but what? This is nothing but one machine cycle. Okay, so this machine cycle is totally dependent on, for different instruction we are having different machine cycles. If the instruction this thing is very much small, then only one machine cycle is required. If the execution of instruction is a bit larger, then it might go from 2 or 4, something like that. Okay, now if you look at this particular scenario, so totally if we are having, if our clock frequency is f, we'll be having 6 different states. Each state requires 2 clock periods. Okay, so total of 6 states is nothing but one machine cycle. Now let us look into the different types of machine cycles. So how many machine cycles are required by different instructions, what and all we are having. So this is the datasheet which we have collected from Atmel. So 8089C51. Now for this instruction set summary, now if you look at this particular this thing over here, okay, so these are our arithmetic operations. Okay, these are our arithmetic operations over here. Now for add, if you take any add instructions over here, okay, for all these add instructions, the oscillator period required is what it is required of 12. Okay, all these particular instructions are required with what it is required with 12 clock periods. The 12 clock period is nothing but what? It is nothing but one machine cycle. In the similar way, if you look at the logical operations over here, we are having different AND operation, OR operation. Okay, now if you observe, certain AND operations require 12 clock periods, that is nothing but one machine cycle. Now if you look at this particular example over here, ANL, if you want to perform AND operation in terms of immediate data, then the number of clock periods required are 24, that is nothing but 2 machine cycles. Okay, so Based on this, if you look at different scenarios over here, we are having different. For subtraction also we are having one machine cycle. If you look at increment operation, again we are having one machine cycle over here. Again for OR operation over here, if you look at this, for OR operation, if you are taking in terms of immediate data, your this thing is 24, so it will be two machine cycles. Okay, in the similar way, if you are having uh, now again for XOR operation, again we are having over here two machine cycle. Okay, now if you observe our multiplication and division operation, the total number of machine cycles required are 4, because the clock period what we are having is here, it is 48. So 48 in the sense total number of machine cycles are 4. Only for what? Only for multiplication and division. Okay, and decimal adjustment is also, it is what, it is 12 clock periods, so it will be what, it will be one machine cycle. So in the similar fashion, we are having what, this is meant for only logical and then arithmetic operation. Now if you look at rotate right with carry, again these are one machine cycle, requirement is one machine cycle. And the data transfer, if you look at the data transfer in inside our 8051, that is required is one machine cycle. And then for direct byte to register, it requires two machine cycle. Okay, so if you want to perform any external data operation, the moment of data to any external memory, then the total number of machine cycles are 2, since our oscillator period is 24. And boolean and boolean expressions, again it is what, again it is one machine cycle. Again if you are performing AND operation, it is going to take two machine cycle. And our conditional assignments, that is jump if carry, jump if no carry, the total number of machine cycles will be what, it will be 24. Okay, so now again for call operations, what we are having, like calling subroutines and all those things, all these particular instructions require total number of machine cycles to be what, it is going to be two machine cycles. Okay, so these are the things where we will get the, we have to find out the data sheet, like from the manufacturer, so how much machine cycle it is going to take. Based on that, we can perform what, we can perform our uh, time delay calculation. If you want to perform any time delays, or if you want to generate any time delays, then this particular, like how much time is required, how much machine cycles are required in order to perform that particular instruction, that is very much important. Without this, we cannot calculate it easily. Okay, but with this, the calculation time will be reduced. Okay, so let us go back to our slides over here. Now if we look at this, let me take, so it so the total time period will be what, here it is going to be what, it is going to be 12. And this clock frequency will be what, it is going to be, let me take this is going to be 11.0592 for 8051, most of the thing, most of the these things. So 12 is nothing but, in order to perform this one machine cycle, so C is nothing but our machine cycle, C is nothing but our machine cycle. So how many machine cycles are required? So that is all regarding that. So let us move on to this thing. Okay, here how here we are having a question. Find the period of the machine cycle for 11.0592 megahertz crystal frequency. Now as we know, let me open calculator. Okay. Okay, we were having what? We were having our clock frequency to be 11.0592 megahertz. Now if I convert, if I divide 0.592 divided by 12, then I'll be getting, oh, sorry, let me get back, 11.0592 divided by 12. So one machine cycle period will be what? It will be in terms of 0.926. Now if I convert that in terms of, since it is in terms of megahertz, then it will be what? It is going to be 921.6 megahertz, okay, kilohertz. Now if I make that like kilohertz, so if I take in terms of 1 divided by 921.600, then I'll be getting what? I'll be getting 1.085 microsecond. Okay, so that is what? So for one machine cycle, the time required is 1.085 microsecond. So that is what one machine cycle time is in terms of 1.085 microseconds. Let us look in some more examples. Now if you look at this, now for a system of 11.052, this is our clock frequency what they have given. So they have asked us what is the time required to complete this particular instructions. Now if you look at move R3 comma hash 55, now if you look at, let me open the same thing over here, our move, that is our immediate addressing mode. So move R3, here this is the thing what we are having over here, this particular instruction. Okay, so move R3 comma hash, this is immediate data. So the total number of clock periods are required are 12. So this is going to be what? This is going to be one machine cycle. Okay, so one machine cycle is required to perform that operation, and again decrement, again it is going to be one machine cycle. So this is going to be one machine cycle, and this is going to be one machine cycle. As we know, decrement, since it is 2, this is going to be 2 machine cycle. Call operation, jump operation, so again these are 2 machine cycle. No operation, so it is going to be taking one machine cycle. And multiplication operation, as we see, this is the largest, so it is going to take 4 machine cycles. Now if you look at the time required, so machine cycle into what? It is going to be machine cycle into the time required. So one machine cycle, it is going to be 1.085, so it is going to be 1.085 microseconds. Here it is going to be 2 into 1.085. So what is the resultant what we'll be getting? That is going to be the answer. Now if we look at the answer over here, so here based on the machine cycles what we are having, we have calculated these things. Here you can observe 2 into 1.085, so I'll be ending up with 2.17 microseconds. Again here I'll be ending with 2.17. Since here it is 4, I'll be ending with what? 4 into 1.085 microseconds, that is going to be 4.34 microseconds. So in order to execute all these operations, it is going to take these many number of time. Okay, so let us look into some more examples. Okay, now if you look at this particular example, find the size of the delay in the program if the crystal frequency is 11.0592 megahertz. Okay, so now if we look at this particular example over here, this is what here we are moving accumulated to with 55 value, and then we are sending that particular value to port 1, and then we are calling delay. The delay as being called over here, again complement, again it is going to jump back to this, and then again there will be what? Again there will be a delay. So it is going to complement this particular port 1 after some delay. Every time after some delay it is going to complement the values in port 1. Okay, so the actual time delay program is present over here. Now if we look at this, move r3 comma hash 200. Okay. uh, Now if you look at this, so it is going to take how many number of times? It is going to execute 200 number of times. Now here if we look at this djnz r3 comma here, so this until it becomes 0, this r3 becomes 0. R3 has been loaded with 200 as of now. It has to decrement to what? It has to become 0. Till that time this loop is going to be executed. Okay, not this part, return part. After execution, after completion of this particular thing, the return part is going to be executed. Now if we look at what is the delay, if we look at this particular operation, now if we have this, now let me take in terms of this here we are performing move operation, so this is going to take one machine cycle, and this is djnz operation, this is going to do two machine cycles. And here we are having, let me take back this thing, let me take a different color. Now if you look at this is going to take how much? This is going to take one machine cycle. This djnz operation, it is going to take two machine cycle. And then here we are having this return operation, again it is going to take two machine cycle. Now if we look at this particular examples over here, this is going to be executed only one time execution. This it is going to execute only one time. Okay, whenever this particular delay program has been called, but this it is going to be executed based on the value what we have put over here. So this particular thing is going to be executed how many number of times? It is going to be executed 200 number of times. Okay, now as we know, our this thing is, now if you look at move operation, it is going to be what? It is going to be 1 into 1.085 microseconds. Okay, now here we are having this here loop, what we are having, it is going to be executed two number of times, and its machine cycle is 2. So here loop or djnz loop what we are having, it is going to be executed how many number of times? It is going to execute 200 number of times, and the machine cycle required is how much? It is 2, and the time required for one machine cycle, it is going to be 1.085 microsecond. Okay, so and again at last we are having return, and then it is going to take two machine cycles, so 2 into 1.085 microsecond. Now let us open up our calculator. Now let me take like this. If we open up this particular calculator over here, it is going to be what? 200 into 2 into 1.085. So I'll be ending up with what? I'll be ending up with 434 microseconds. Okay, so this is going to be 434 microseconds, and let me take my, it is going to be 434 microseconds. Sorry for this. Okay, next is what? 1.085, and this is going to be 2.17, right? So 1.085 into 2 if we do, so I'll be getting what? 2.17. So if we perform this operations over here, if I take this particular thing, so this is going to take how much? So this is going to take, let me use screen, so this is going to, this is what? This is how much? This is going to be 1.085 microseconds. Okay, and this is going to be 434 microseconds. Okay, and this is going to be 2.17 microseconds. If we add up all these things, okay, let me add up all these things over here in the calculator. So 2.17 plus, take this, 17 plus 1.085 plus 434. If we add up all these things, we will be ending up with what? 437.255. So the value what we are getting over here, it is going to be 437.255. Okay, so this 437.2.5, it is in terms of what? It is going to be in terms of microseconds. Now if I will convert this to what? If I convert this into milliseconds, so I'll be getting what? I'll be getting 0.4 milliseconds. Okay, so the time delay for this particular, so the time delay for this particular operation what we are having over here, it is going to be what? It is going to be 0.4 millisecond. Okay, so let us look into, this is how we are going to calculate. First you take the delay, which is, take the time required to complete this instruction. Since this is going to be only one time, so I'll be taking this particular as only one time, and the return instruction, it is going to be one time as well. The loop is present over here, this particular loop. Okay, now this particular loop is going to be executed, the value what we are going to load here, since we have loaded with 200, so this loop is going to be executed 200 number of times, and the number of machine cycle required for this particular loop is going to be 2. So 2 into 200 into 1.085. Okay, so that value we are going to get somewhere around 434, and this is going to be 1.085 micro, and this is going to be 2.17 micro. If we add up all these things, I'll be getting 437.255 microseconds. If we convert that to in terms of milli, so I'll be getting 0.4 millisecond. Okay, so let us look into some more program. Let's see. Okay, here again we are having the same problem over here. Let us, what we should do, first I need to find out, so what is the thing what we need to perform. So this is going to be executed only one number of time, and no operation, no operation, so this is going to be one number of time. This is going to be one machine cycle. Again this is going to be one machine cycle. Again this is going to be one machine cycle. Here we are having DJ and Z, so this is going to take two machine cycles. Okay, and this is going to take again two machine cycles. Okay, so now if we take a look at this, this is what, this is our loop what we are having. This is going to execute 250 number of times. Okay, this is the loop what we are having. So if we are having 252, inside 250, how many machine cycles we are having? We are having 1 plus 1, 2, 3, 4, 4 plus 2, 6. So 6 machine cycles. So 250 into 6. Okay, 6 machine cycles. And this is going to be a what? It is going to be multiplied with 1.085 micro. Okay. Now if you look at this, this is going to be 1.085, since again this is going to be 1 into 1.085 micro. Okay, and this particular, this thing is going to be executed only once. So again I will not write 1 into, so number of machine cycles, it is going to be 1.085 micro. Okay, So what is the time required for this? Let us calculate. So let me open up the calculator again. So it is what? It is 250. So let me clear this history. It is going to be what? It is going to be 250. 250 into 6 into 1.085 micro. Okay, so I'll be getting what? I'll be getting the value 1627.5. So we'll round off this to 1628. Okay, so this is going to be 1628, and next is 1.085, and then plus, so this is 1627.5. So let me round this up to 1628. So I'll take 1628 plus 1.085 plus 2.17. So I'll be getting somewhere around 1631.255. So all these together I'll be getting 1631.255. So let me come back to this particular thing. So all these, if I add up all these values, I'll get how much? 1631.255. I'll be getting 1631.255. Okay, 255 microsecond. If we convert this particular thing into milli, so I'll be getting what? I'll be getting something like 1.63 millisecond. So the total delay offered by this particular block is how much? It is going to be 1.63 milli. Okay, so if you want to increase delay, one thing what we can do, we can use these NOPs what we are having, no operations. I can use these as many times as want. If I want to increase delay, I need to increase this NOP. Or what we can do, see here we are having what we are having, this R3 register what we are having over here. The maximum value what I can load to this particular, since our registers are only 8-bit, the maximum value I can load, it is going to be 255. Okay, I cannot load more than 255 because the number of bits is going to be increased. So in order to, if I want, see it is here we have loaded with 250, and the value what we are getting, it is almost 1.63 milli. It is only, still it is in terms of milli. But if I want in terms of seconds, if I want delay in terms of seconds, or if I want somewhere around delay to be 500 millisecond, okay, or if I want somewhere around 100 milliseconds, this register is insufficient. At that time what we are going to do, we are going to use our nested loop operation. Okay, so nested loop operation is nothing but what it is. Here what we are going to do, we are going to use two different loops, and then we are going to increase the delay. Now here if we look at let us try to find out the program over here. Now here for this thing, it is going to be executed only one number of times, so I'll be using 1 into 1.085. okay, and here again it is going to be 1 into 1.085. okay, our NOP operation, again it is going to take one machine cycle. Okay, and again here NOP operation, again it is going to take one machine cycle. This is going to take two machine cycle, and again it is going to take two machine cycle, and again it is going to take two machine cycle. Okay, now if you look at this, this is what, this is going to be executed once, this is once, and this is one machine cycle, this is again one machine cycle, two machine cycles, two machine cycles, and then two machine cycles. Again here what it is going to do, it is going to be executed what, it is going to be executed into 1.085. Okay, that will be equal to what? 2.17. Okay, now this, if we look at this particular operation we are having over here, this is going to execute, this loop is going to be executed how many number of times? Since it is R3 over here, DJNZ R3, so this is going to be executed 250 number of times. Okay, this is going to be executed 250 number of times. And if you look at this particular operation like this, since it is a nested loop, okay, again we are looking in terms of what? R2, so this is again executed 200 number of times. These particular loop operations are going to be executed what? Let me take. Okay, so these particular operations what we are having, these loop operations, they are going to be executed 200 number of times. Since I have called this particular loop again, this is going to be executed 200 number of times. So total machine cycles are required here. If you look at this, it is going to be, let me take in terms of red color itself. For this particular operation, let me take in terms of red. Okay, it is going to execute how many number of times? It is going to execute, nope operation is what? It is 1 plus 1, so it is 2. 2 plus 2, it is going to be 4. So 4 into 250, this into how many number of times? Again it is going to execute 200 number of times, so it is going to be 200 into 1 point what? 085, that is going to be how much? If we look at this, let me take in terms of be clear, it is going to be 4 into 250 into 200 into 1.085, so I'll be getting 217,000. So this is going to be how much? This is going to be the offered by this thing is going to be 217,000. Okay, plus these instructions what we are having, 1.085 plus 1.085 plus 2.17. okay, so what I'll be having, if we look at this, let me open up the calculator again. So 217, so plus I need 1.085 plus 1.085 of move R3 comma hash 250 plus the return instruction what we are having, it is going to take 2.17 microseconds. So the total this thing is 217,004. Let us round off it to next higher value what we are having. So it is going to be what? It is going to be, if we take in terms of what, if we take in terms of this thing, it is going to be 217,005. okay, so this is what it is, how much it is going to be in terms of what? In terms of microsecond. Now if you want in terms of millisecond, this, the time offered by this is going to be what? It is going to be 217 millisecond. Okay, if you convert again this in terms of second, it is going to be what? It is going to be 0.217 second. Okay, this is how, like here you can observe, we have achieved, by this we have achieved 0.217 second as a delay. That means 217 millisecond as our delay by using what? By using nested loop. Okay, again here what you can observe is that we have achieved this total 250 and then again 255. Again if you want to add still more delay, again what you will be using, again you will take the nested loop and you will be taking in terms of, again you will be loading one more register with some value, and then you are going to increase this loop by using nested loops. So based on this, how this is how we are going to calculate the delays in terms of 8051 microcontroller. Now if we look at this in the all these slides, actually we were given with a program and then we need to find out the delay. Okay, but the scenarios are not different. Suppose if I want to generate 1 millisecond of a delay, so what should I do? Okay, so here, so how should I write down a program in order to generate a delay of 1 millisecond? So that is totally dependent on what? It is totally dependent on our clock frequency. Okay, so first what we are going to do, if we look at this, we are going to perform our clock frequency. What we are having, it is going to be 11.0592 divided by 12 we are going to do. So again I'll be getting some 0.927.2 something like this kilohertz. Okay, this I'm writing in terms of assumption. Okay, this we had actually seen in our previous slide. So 927, again what I'll be doing, I'll be dividing 1 divided by 927 kilohertz. So I'll be ending up with what? I'll be ending up with 1.085 microsecond. So this is the time offered by what? It is the time which is offered by one machine cycle. Okay, so keeping this as my reference, what I'm going to do is I'm going to calculate my how many machine cycles are required in order to generate 1 millisecond. Okay, now if we look at this, if I do 1.081 millisecond divided by 1.085, then I'll be getting what? I'll be getting my actual count. So let me open up the calculator again. So we look at this, let us see this operation over here. Let me move back to standard calculator. Okay, now it is 1.01 millisecond. Okay, so let me take that in terms of 1000. So 1000 microseconds is here 1000 microsecond is nothing but 1 millisecond. So 1000 microseconds divided by 1.085, so that is 1.085. So the total number of these things count I required in order to perform that much of delay, in the sense I need 921 should be the count. Okay, out of this 921, the loop what we are going to have is we take in terms of the machine cycle required for DJ and Z. If you take the machine cycle required for DJ and Z is how much? It is DJ and Z. Let me DJ and Z. It is going to be how much? It is going to be 2 machine cycles. Okay. So and then if I use one knob operation, so I'll be getting how much? I'll be getting 1 machine cycle. This is 921. It is almost equal to what? It is going to be almost equal to 1000. Okay, now if I add up these 3 into 3, since I cannot load 300 into my register, the maximum value I can load this thing to my register is going to be what? It is going to be 255. Okay, so let us see what is the value what we are getting. So 921. So if I use one more knob operation, so that I can have what? I can 921 divided by 4 if I do, so I'll be getting which is the value which is going to be lesser than 255. Okay, so here these are the loops what we are going to be executed in terms of a loop. Now if you look at this 921.65, if I divide it in terms of 4 machine cycles, the value what I need to load into my register, it is going to be what? It is going to be 230.4. So since it is 0.4, what we should do, we should be loading our value with what it is going to be, what it is going to be 231. Now if you look at our delay program, so what here I'll call delay. So what I'll be doing, so let me change the color over here. Okay, delay. Okay, so this first what I'll be doing, I'll be moving some register R3. Okay, let me load this R3, move R3. Since I got 230.4, I'll be loading the value with what? I'll be loading the value with 234. Okay, to 230.4 something I got, so I'll be loading with, let me check the, yes, it is 230.4, so I'll be loading the next higher value. Okay, so that is going to be what? That is going to be 231. So next here, let me write it as here. So I'll be loading, this is going to be one machine cycle. So here, and then first is what? Let me call this no operation. So again, no operation. Again what? Again no operation. Okay, so next it is going to be what? Next it is going to be DJNZ R3 comma what? R3 comma where it should go? It should go back to here. So then again it is going to be return. So this is how, if we look at this, if you look at this particular operation, let us check whether it is going to be correct or not. So now if we look at our, let us go in our conventional way, this is going to consider, if you look at this is going to take one machine cycle. Okay, again this is going to take one machine cycle, this is going to take one machine cycle, this is going to take two machine cycle, and this is going to take two machine cycle. So this I'll be getting my time to be what? I'll be getting, since it is only executing one time, so it is going to be 1.085 microsecond. Okay, and then this is going to be executed only once, so I'll be getting what? My this thing will be 2.17 microsecond. Here the number of machine cycles are 4, so these are going to execute 231 number of times, so this is going to be 231, and the time required for one machine cycle, it is going to be 1.085 microsecond. Okay, so let us try to calculate this. Let me open up our calculator again. Okay, so this is going to be 231 into 4 into 1.085. So I'll be getting what? I'll be getting 1002.54 plus 1.085 plus 2.17. So the value what I'm getting here is, it is going to be what? 1005.7 or 1006. If we add up all these things based on this thing, if I add up all these values, the values what I'm getting is 1006 microsecond. If you convert that into milli, so it is going to be what? It is going to be 1.006 millisecond. So I'll be getting 1 millisecond. So this says that our program what we have written, it is going to be same. So first what you need to do, first we are going to calculate the value which is required for one machine cycle, and we are going to divide the required delay with this delay. So required delay, so it is going to be what? It is going to be the formula is going to be what? It is going to be what? it is going to be required delay divided by our 1.085 micro. Okay, micro. So this gives us what? This is going to give us some value. So that value will be what? That value will be our count. From this we are going to find out what should be the count. How many number of machine cycle, how many number of DJ and Z I need to include, how many number of no operations I need to include. Based on that, we are going to get this count value. Okay, this is actually the count what we are going to have. So that count, based on these operations, I'm going to put that into my register over here. This is how actually we are calculating our time delays. Okay, in the this is all regarding into simple assembly level programs using loops, how actually we'll write down the programs. Till then, bye. Thank you.